trying to help those of you who are still struggling on the waves background worksheet get caught up. So I thought this would be a fun place to do a video on wave background. This is my son's bedroom mural I made for him a few years back. Anyway, and it shows you some waves, right? So today we're going to talk about how waves carry energy, and they carry energy through matter. So we're going to talk about the waves carrying energy as well as the interactions that they might have with that matter. So first of all, we have two types of waves and they carry energy a little bit differently. So the first type of wave is a transverse wave, and what that means is that the energy is moving in one direction, but the matter that it's moving through moves in another direction. So it's moving up and down, the matter's moving up and down, and the wave moves forward. So this is a transverse wave. Notice the slinky goes up and down while the wave goes this way. That type of wave has crests and troughs. So the water that you see in the background, you can see the little crests of the waves, right? Painted with the little, let's see if I can match it up with my fingers. There's one, there's one, there's one, right? So those are your crests. Now the distance between those crests would be your wavelength. So how long each wave is. Now how high they are, how much they rise up from where they were when the water was level, that's called your amplitude. Anyway, the amplitude helps you understand how much energy is being carried by a wave. So you know that if you have like a 40-foot wave coming at you, that's got a lot more energy than say a 20-foot wave coming at you, which still has a lot more energy than like the little teeny half-foot waves. Okay. Now this is a compression wave or a longitudinal wave. But you have areas where the slinky gets compressed and areas where it is spread apart. So the areas where it's compressed, easy enough, are called compressions. And the areas where it is stretched out are called the rarefactions. So the distance between one compression to the next compression is the wavelength, just like in the transverse wave. And then the amplitude, or the amount of energy in the wave, is described in that case by the size of your compression. Notice that to make both of these waves, I have to move my hand. For the transverse wave, I have to move my hand up and down at a right angle to which way the wave goes. And in a compression wave, I have to move it forward and back. But either way, to start a wave, I need some kind of vibration.
The PhET simulator is an awesome way to see how waves interact on surfaces. So here's water drops. You can see the waves propagating, moving through the water surface. The blue lines represent the wave crests, and the black areas are the troughs. Now if I move the frequency slider all the way to the maximum, you can see that the water drops are hitting more often. And as that happens, the waves are getting closer together. So that means the wavelength, or the distance between the crests, is getting shorter. Now, as I move it back down, you see that the wavelength is getting longer and the frequency is getting lower. PhET has some pretty cool tools. This one is a water level meter. So it tells us what the water level is at any point. Now, if I put this sensor farther away from the source and then this one closer to the source, you can see the difference in the wave heights, or the amplitude of the wave. So as you're closer to the source, the amplitude is much higher. As you're further away from the source, the amplitude's much lower. That's because the energy of the wave is getting spread out as the wave moves in a larger and larger circle. Now let's look at sound waves. So as we move this PhET simulator to the sound tab, we can see that when we start playing a sound, It looks very much like when the drops of water hit the surface. So there's a vibration in the speaker that's causing the molecules in the air to get compressed and then to spread apart. We call those areas where they're spread apart rarefactions, and areas where they're compressed compressions. Again, if I move the amplitude slider to the right, to the maximum, you can see that the compressions get much bigger. Now let's look at the frequency of the wave. If I move the frequency slider up to the maximum, you can see that the waves get much closer together, and more of them will pass a point in a given second, even though the wave's speed is the same. The speed of the wave is determined by the medium, and so if the frequency gets higher, then that means that the wavelength gets lower, and vice versa. If the wavelength gets higher, then the frequency gets lower. So speed is equal to frequency times wavelength for any given medium. So far, we've been looking at mechanical waves. The slinky, the water, the sound waves, these are all waves that require matter. Now let's look at light waves. Light waves don't require matter. They're what we call electromagnetic waves. When you turn on a light, a charged particle or a bunch of charged particles start vibrating, and that disrupts the electric fields and magnetic fields around that object. So that's what we call an electromagnetic wave. Visible light all around us is actually made of electromagnetic waves. So white light that we see from the sun is actually made of all the colors of the rainbow. Red light has the lowest frequency and the longest wavelength. If I move the frequency slider to green, you can see that the wavelengths are shorter and the frequency is higher. But again, the wave moves at the same speed. If I keep moving the frequency slider up, you see that I get to violet, where the frequency is very high and the wavelengths are very short. If I were able to move the frequency slider even further, I would get into light that we can't see. That would be called ultraviolet. Beyond that would be X-rays, and beyond that would be gamma rays. These are all forms of electromagnetic radiation. Visible light, or what we can see, is only a tiny fraction of the entire electromagnetic spectrum.
Jack, are you feeling very educated about waves?
You want to see what you look like in low frequency light? Here's Jack in infrared light. His nose and his toes are blue because they are colder. The yellow areas are places where he's warm. Infrared is heat radiation. Looks like Jack left some heat radiation on the carpet. What's this square on the carpet? Oh, it's just the radiation coming from the window heating up the carpet. I can use this heat camera to check out lots of cool things in my house. Like, look, you can see the heat coming from the refrigerator. You can tell that I just used the oven. To learn more about the electromagnetic spectrum, please check out NASA's website that I've linked in Google Classroom.
Okay, Jack, next we're going to talk about wave interactions. What happens when waves hit stuff or hit each other? So one type of wave interaction is reflection. So right now you're actually looking at a reflection of me rather than the actual me. So the light looks like it's coming straight from me to you, correct? But really it's coming off of me, hitting the mirror at an angle, and then bouncing off at the same angle but to the opposite direction and heading straight for the camera.
The equal angles law of reflection applies no matter what the shape of the mirror.
Reflection. Here's an example of diffraction where light is bending around a doorway. So the doorway is the opening and the light is the wave, and as it goes through that opening, it bends around the barrier. As you can see on the floor, it's spreading into the room. So refraction then is the way that light bends as it goes through different materials. So when it hits a material where it has to slow down, but yet still is able to make it through, then it will bend. So, or if it speeds up, if it changes speed at all, it will bend as it does that. So as light hits a window, let's say, the window glass is harder for it to penetrate through, so it's going to bend as it goes through there. And then when it goes back out and into the air on the outside, then it will bend again. And so you can see interesting effects with that phenomenon. So for example, so we have this glass jar, right, filled with water. And if I take a couple of arrows and pass them through, you see that the arrow on the bottom switches direction, right? That's because the light is bending.
The light waves are so bent that they actually cross on the other side and make it look like it's backwards.
So lenses, we use them for all kinds of things. Camera lenses, microscope lenses, telescope lenses,
and eyeglasses.
Just filling up a sink, I can make waves in the bottom of the sink, right? Now you can see as the waves reflect off of the surface of the sink, they actually start to interfere with each other and you get really interesting little patterns. So those are what we call interference patterns, where the crests line up with each other, they actually amplify and add together, and where the crests line up with the troughs, they cancel each other out. And so you get these funny little patterns. Now that we've learned a little bit about waves, let's go back and talk about sound. So sound waves, remember, are produced by vibration and they move matter. So when we have something like a guitar, when we're vibrating the string of a guitar, if it vibrates very quickly, that means it has a pretty high frequency. If it vibrates very slowly, that means that it's going to have a low frequency. Less waves will pass a point per second if it has a low frequency. So there's a couple ways to do that on a guitar. So first of all, we have heavy strings and we have light strings. So a heavier string is going to produce a lower note than a light string. So a heavier string has more inertia, which causes it to resist changes in motion, which means that it vibrates much slower. A lighter string has less inertia, so it's going to vibrate much faster. So those higher frequencies mean higher pitches. Now another way that we can increase the frequency is by shortening the string. So if I start with a nice long string and I pluck it, you hear a low note. I can shorten the string by pressing down and moving my thumb inward.
Shorter strings vibrate quicker, so have higher frequencies.
I can make a quick pan flute with just a series of straws. So I have a long straw, a medium straw, and a short straw. Now, if I blow into each one, the column of air inside is going to vibrate at a certain frequency. So let's check it out. So all the same materials, but yet, because of their different lengths, they're going to vibrate at different frequencies.
Have you ever paid attention to how a car sounds when it passes by? First it gets louder, of course, but it also gets higher in pitch and then lower in pitch. That's due to something called the Doppler effect. The waves get bunched up as the car approaches, and then they spread back out as it moves away.
Now let's say I record myself counting from 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I speed that video up.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And then I slow that video down.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
What do you notice about how it sounds? Why do you think that is? Well, when you speed it up, the sound file gets all cramped together, right? So the frequency of the sound is much higher. When you slow the video down, you spread the sound file out, and so the frequency of the sound gets much lower. So how do we hear? Well, your pinnae, or the outer ear, funnels the sound into your ear canal, which vibrates the eardrum. The eardrum then vibrates the ossicles, or the little bones in the middle ear, called the hammer, anvil, and stirrup. The stirrup then vibrates the cochlea,
which has little hairs inside that stand on end when it picks up noises. Those send auditory signals to the brain through the auditory nerve. The semicircular canals are for balance. They're filled with fluid that can move as your body moves to tell your brain if you're off center. So how do we see? Well, first the light has to get into our eyes and then project an image onto the back surface called the retina. The cornea is the outer surface of the eye and it focuses the light. So when your eye is misshapen, corrective eye surgery can reshape your cornea and allow you to see more clearly. Once the eye passes through the cornea, it enters the eye through the pupil. The iris can open and close the pupil to allow just the right amount of light in. Once through the pupil, the light will pass through the lens, where it's refracted even more so that the image is focused directly on the retina. The retina is made up of rods and cones. Rods help us see in low light conditions. Our cones help us see color. We have red, blue, and green cones. They're sensitive to those particular frequencies. They send the images to the brain, and then the brain makes sense of it, mixes the colors, and helps us see the full spectrum. Not all animals are as limited as humans. The mantis shrimp, for example, has 13 color cones. All right, so that should give you at least a little background so that now you guys can go out and do your own projects. Learn more about waves, light, and sound, whatever interests you the most. Look forward to hearing from you. Hello, come to my Google Meet.